Hello and welcome to this video about functions. In this video, we'll take a closer look at what a function is and how a function can be defined formally. So what is a function? You have probably seen the following definition of a function. A function f from x to y is an assignment that to each element x in x assigns an element y in capital Y. And the element small y is denoted f of x. It's called the value of x. Perhaps a problem with this definition is that the notion of assignment is not precisely defined. It is a useful definition that is reasonable to think about in most contexts, but perhaps you've asked yourself, how can we make this formal? And the answer to that question is relations. So what is a relation? A relation from a set x to a set y is just a subset R of the product set x times y. So R consists of some set of pairs of elements with x in x and y in y, satisfying some conditions defining R. So a bit of notation and terminology. If the pair x, y does belong to this subset, we say that x is related to y, and we often denote this x, r, y. So what does this have to do with the intuitive notion of a relation? Let's consider some examples. The first example is the relation x is smaller than y. Let's take as our set x the set consisting of three numbers, 1, 3, 4, and the set y the set of consisting of two numbers, 2 and 5. So if we draw this product set, we have 1, 3, 4 on the x-axis and 2, 5 on the y-axis. And we then have the product set as the set of pairs consisting of these numbers. So this point is, for example, the pair 4.2. The pair 4.2. So now the relation tells us which elements actually satisfy x smaller than y. So 1 is smaller than 2, 1 is smaller than 5, 3 is not smaller than 2, but 3 is smaller than 5, and 4 is not smaller than 2, but 4 is smaller than 5. So our set R consists of those four pairs of numbers, where the x-coordinate is smaller than the y-coordinate. Another relation, let's say the relation from the real numbers to the real numbers, defined by y equals x squared. So we say that y is related to x if y is equal to x squared. And so now, what is a function? A function, formally, from x to y, is a relation f from x to y satisfying one additional property, namely each x is related to a unique y. So for each x in x, there is a unique y in y such that x is related to y. So this, if this had been in our previous slide, we would have denoted this x is related to y through the relation f. But instead of writing that, and instead of writing x, y belongs to f, commonly one writes y is equal to f of x. This makes sense because of this condition that to each x, there is a unique y related to it. And that's why we can write y equals f of x. Let's look at some examples. The previous example of 1, 3, 4 and 2, 5 does not satisfy this definition because the element 1 is both related to 2 because 1 is smaller than 2 and to 5. 1 is smaller than 5. The elements 3 and 4 are related to one element each, but this doesn't help because we have one element that is related to 2 elements. If instead of 4 we had 6 here, let's say, then we would have another bad thing that happens, namely that x equals 6 is not related to any y. So this is not a function. The relation y is equal to x squared is, on the other hand, a function. So this is the case because, yeah, to each x, x is related to x squared. So x is related to precisely one y, namely y equals x squared. On the other hand, if we look at the relation that x is equal to y squared, this is not a function. It does not satisfy this property because if we take x equals 4, then x is on the one hand equal to minus 2 squared and on the other hand to 2 squared. So it is related to 2 different y's. So this is not a function. So of these 3 examples, this is the only function. So a function is a relation from x to y, such that for each x in x there is a unique y in y related to it. Note that this says that to each x there is exactly one function value y. It doesn't say that each y is the value of exactly one x. Indeed, these are the notions of injective, surjective, bijective that you have seen in other contexts, hopefully. So we call a function f injective, surjective, or bijective if to each y there is at most one, at least one, or exactly one x with y equals f of x. So this definition might seem a bit strange, but as you might guess, there is a geometric notion that is familiar and that this portrays. So remember that we defined a function as a relation from x to y. So this is a subset of x times y. What is this subset? Well, this is the graph of the function f. So if we look at this example, this was our function f from the real numbers to the real numbers, defined by f of x equals x squared. So seen as a relation, this is the set of all pairs xy such that x squared is equal to y. And this is precisely the graph of the function f, because what is the graph? The graph consists of all pairs of points where or pairs of numbers in this case, where y is the function value of x. So in other words, if you take the familiar definition of a function, and from that, the familiar definition of the graph of a function, this is exactly it. The graph of a function consists of pairs of points where the first point is in the domain and the second point is in the codomain. And so the formal definition of a function is nothing other than the definition of a graph of a function, in a sense. Let us now look at sets of functions. So if you have a set x and a set y, you might want to consider not one specific function from x to y, but the set of all functions from x to y. This is denoted y to the power x. We'll see soon why, but let's, no pun intended, let's look at some examples. So let's look at the set 0, 1 to the power abc. So this is the set of all functions f from a, b, c to the set 0, 1. So for example, we can have f of a equals 0, f of b equals 1, and f of c equals 1. So that is one element of that set. And you can interpret this specific example in a certain way. So you can interpret 0, 1 as no and yes. So a function from a set to 0, 1 just tells you for each element in the set no or yes. And this can be interpreted as constructing a subset. So functions from a set X to the set 0, 1 are in correspondence with subsets of the set X. Namely, which elements should I include in the subset? Well, all those that give the value 1 and exclude the value, those that give the value 0. So this corresponds to the subset BC. And this brings us to the power set 2 to the power x. That's the set of all subsets of x, which can be viewed as a special case of the previous type of example, because this would be considered as the set of all functions from x to the set 0, 1. The set of functions from the set with one element, let's denote it 1, to a set y is in bijection to y. Why is that? Well, a function from the set 1 to y is just a choice of one element in y to which you map 1. If you think a bit about these examples and how many elements they have in the cases where the sets are finite, you arrive at the following proposition, that if the set X has m elements and the set Y has n elements, then the set of all functions from X to Y has n to the power m elements. Because for each element in X, you need to choose one of n elements in Y to map it to. I leave it as an exercise to do the calculations and convince yourself about this result, which motivates the notation. Finally, we can ask, what is the set of all functions from the empty set to the empty set? There is a unique function from the empty set to the empty set because it is an empty condition to specify what the function should do. And so according to this philosophy, 0 to the power 0 should be equal to 1. The number of functions from the empty set with 0 elements to the empty set with 0 elements. Sometimes you're not interested in all functions from x to y, but functions that preserve some additional structure that you might have. Let's touch very briefly upon this. As you might know from linear algebra, if you're looking at not sets, but vector spaces, let's say real vector spaces x and y, so these are sets with additional structure, then you're not interested in all functions from x to y, but linear maps from x to y. So these are functions from x to y that are required to respect the addition and the scaling. So if you add two elements in x, before applying the function, it should give you the same result as applying the function and then doing the addition in y, and same with the scaling. And in different branches of mathematics, where you are working with not sets just, but sets with additional structure, you limit yourself to functions that in a similar way respect this structure. In the case of linear algebra, you're looking at linear maps between vector spaces. If you're studying topological spaces, you consider continuous maps between topological spaces, not all maps. If you are in algebra working with groups or rings, you consider group homomorphisms or ring homomorphisms instead of all functions, and so on. And this brings us to the end of this video, where we have explored the notion of a function and different uses of different sets of functions.